addressing modes, and this is used to specify the branch addresses in a call or a jump instruction. During these instructions, one has to specify the location to which program control is to be transferred. There are 4 types of addressing modes. The first one is the intra-segment direct addressing. Intra-segment addressing means the location to which control is to be transferred is within the current code segment. And direct addressing means the displacement of the location is specified within the instruction itself. Now, if the displacement is an 8-bit displacement, it is called a short jump or a short call. And if the displacement is 16-bit, then it is called a long jump or a long call. Now, during an intra-segment direct addressing scheme, the format of the instruction is like this. You specify opcode followed by the displacement. Effective address is computed as the sum of the contents of the instruction pointer and the displacement. So an example is this. JMP is the mnemonic for the jump instruction, and you specify a displacement after that. And the displacement could be an 8-bit displacement or a 16-bit displacement. Intra-segment indirect addressing. Indirect addressing means the branching address is not specified within the instruction itself, rather it is contained in a memory location or in a register. Now, the memory location holding this effective address can be specified by any valid data addressing. For example, consider this instruction: jump, then displacement and dx. So this is an example of a based addressing scheme in data addressing. Now, the effective address of the branch is given by bx plus displacement, and this value will be placed in the instruction pointer so that the program control can be transferred to that location. The next is inter-segment direct addressing. Now, inter-segment means the branch location is not within the current segment. It is in a different code segment, and therefore when we specify that address, we have to specify both the segment address as well as the displacement, the offset. So it requires 4 bytes. Now, if those 4 bytes are specified within the instruction itself, it is inter-segment direct addressing. As an example, consider the following jump instruction: jump followed by a 4-byte immediate value. The first 2 bytes will go to the instruction pointer, and the next 2 bytes will go to the code segment register. So the effective address can now be computed using the CS register and instruction pointer. Next is inter-segment indirect addressing. In this case, the branching address is not within the current segment but in a different code segment. The address of the branch is specified not explicitly within the instruction but by a memory addressing scheme. For example, consider the following instruction: jump, and then the memory address is specified by a based addressing scheme. Now, bx plus displacement will give the address of the memory location which holds the branch address. At that location, the first 2 bytes corresponds to the value to be stored in the instruction pointer, and the next 2 bytes correspond to the value of the code segment register. Once this transfer has been made, CS together with instruction pointer provide the branching address. 8086 has a large number of machine instructions, and they are arranged using an instruction format. An instruction can be 1 to 6 bytes long. The first byte contains the opcode, which may be 6 bits or 8 bits long. If the opcode is 6 bits long, the remaining 2 will have a meaning according to the specific instruction. Now we consider the template of a move instruction. Move instruction is used to transfer data from a source to a destination location. Now this move instruction usually have up to 6 bytes length. The first byte contains opcode, and the opcode for the move instruction is only 6 bits long, and therefore there are 2 remaining bits in the first byte. Opcode occupies the 6 most significant bits, and bit numbers 1 and 0 correspond to 2 fields called the direction field and the word field. Byte 2 specifies the 2 operands. One of the operands could be a register, and that can be specified by the reg field, which has 3 bits. The other operand can be specified together by the mode field, which has 2 bits, and the rm field, which has 3 bits. Now, if the register specified by the reg field is the source, then D has to be set to 0. Whereas if D is equal to 1, then the operand specified by the reg field will be the destination, and the other operand specified by the rm and mode fields together will be the source. If the size of the data to be transferred is a byte, then W should be set to 0, and if it is a word, that means 2 bytes, then W field should be set to 1. Now, the move instruction may use a memory addressing to specify the address of the memory locations. It may involve a displacement, and byte numbers 3 and 4 hold the values of the displacement. The lower byte of the displacement will be in byte 3, and the higher byte of the displacement will be in byte 4. Now, if you are using a direct addressing scheme, then the direct address is specified in byte numbers 5 and 6. Here again, the lower byte will be in byte number 5, and the higher byte will be in byte number 6. Encoding of reg field. Reg field specifies the register in the move instruction. If the size of the data transferred by the instruction is a byte, then the register specified by the reg field should also be of size 1 byte. Similarly, if the data transferred is a word, then the size of the register should be 2 bytes. Now the encoding is done according to this table. If reg equal to 0, 0, then for W equal to 0, the register specified is AA, and for W equal to 1, the register specified is AX. Now for 0, 0, 1, they are CL and CX, and 0, 1, 0, they are DL and DX, and for 0, 1, 1, they are BL and BX. For 1, 0, 0, the register specified when W equal to 0 is the AH register, the higher byte of the AX register, and for W equal to 1, that is the stack pointer SP. Now for 101, the registers are CH and BP, and for 110, the registers are DH and SI, and for 111, the registers are BH and DI. The next is encoding of RM field for mode field equal to 1, 1. When mode field is 1, 1, the RM field specifies a register. That is, the second operand in the move instruction will also be a register. For mode equal to 1, 1, the encoding of the RM field is similar to the encoding of the reg field. That is, if RM is 0, 0, 0, And for W equal to 0, it specifies the AL register, and for W equal to 1, it specifies the AX register, and so on. Now we consider the encoding of RM field for mode equal to 0, 0, 0, 1 and 1, 0. In these modes, the second operand will either be a memory location or a direct address. In mode equal to 0, 0, when RM is equal to 0, 0, 0, the address of the memory location is specified by the sum of the BX register and the SI register. Now for mode equal to 0, 1, the address is specified by BX plus SI plus an 8-bit displacement. And for mode equal to 1, 0, this is BX plus SI and a 16-bit displacement. And therefore if you look in the table, you can see that mode equal to 0, 1 correspond to addressing with an 8-bit displacement, and mode equal to 1, 0 correspond to addressing with a 16-bit displacement. So now RM equal to 0, 0 correspond to based index addressing. So the effective address is the sum of the contents of the BX register and the SI register here. Now mode 1, 0 correspond to based index addressing with displacements, 0, 1 corresponding to 8-bit displacement and 1, 0 corresponding to the 16-bit displacement. Now for RM equal to 0, 0, 1, mode 0, 0 correspond to an addressing with BX plus DI, and mode 0, 1 and mode 1, 0 correspond to the same addressing scheme with the displacements, 8-bit displacement and 16-bit displacement respectively. Now RM equal to 0, 1, 0 will have an addressing given by BP plus SI, and RM equal to 0, 1, 1 will have an addressing scheme with BP plus DI giving the effective address. Now RM equal to 1, 0, 0 will have SI index giving the address, and RM 1, 0, 1 will have the destination index giving the address. Now if RM is 1, 1, 0, then the address is given directly in the instruction, and RM equal to 1, 1 correspond to address given by the BX register. Sometimes one may have to use a segment different from the default segment. In that case, one can use a prefix called the segment override prefix to override the default segment. This is used as a 1-byte prefix to the instruction. Now the structure of that 1 byte is given by this diagram, where only the bits 3 and 4 will encode the segment that is to be overridden. Other bits will be fixed by this template. Now the encoding is given by this table. If the bits S and R are 0 and 0, then the segment to be used is ES, and if SR is 0, 1, then the segment is CS, and if SR is 1, 0, segment is SS, and if SR is 1, 1, the segment is DS. Now instruction pointer and stack pointer can only be associated with their default segments, the code segment and the stack segment respectively. In some string instructions where DI is used as the implied pointer for the destination string, then it can only be associated with the extra segment. Now we consider some examples. First, consider the instruction move BL, CH. This instruction means move the contents of the CH register to the BL register. So the source is the CH register and the destination is the BL register. The size of the data to be transferred is 1 byte, and therefore the W field should be 0. Now the source is a register and can be specified by the reg field, and therefore we should set d equal to 0. D equal to 0 means that the location specified by the reg field is the source. Now reg field should encode ch, and if you look back you can see in the encoding of the reg field that ch register is specified by reg field value 101. Therefore we have d equal to 0, w equal to 0, and reg equal to 101. Now the destination is also a register and it is BL. Now therefore the mode and RM field together should specify the register BL. If you look back you can see that mode equal to 11 specifies a register and RM equal to 011 specifies the BL register. 011 specifies the BL register. So we have mode equal to 11 and RM equal to 011. Putting them all together in the template, we have the first byte will have the most significant 6 bits specifying the opcode, which is given by 100010. Then the direction bit is 0, W bit is 0, then mode should be 11, reg should be 101, and rm should be 011. Now we write them as a hexadecimal number. For this we split them into nibbles and write the corresponding hexadecimal digits. So you have 8, 8, E and B. So the machine code for the instruction move BL, CH is the hexadecimal number 88EB. The next instruction that we consider is this one, move 1234 SI, AX. Here the source is the AX register and therefore can be specified by the reg field, and the size of the data transferred is 1 word and therefore W should be 1. Since the register specifies the source, D can be set to 0 and reg equal to 000 specifies the AX register. Now the destination is given by 1234 SI. So the location is given by an offset address SI plus a 16-bit displacement. So the specification of the memory with an offset address of SI plus a 16-bit displacement should be encoded by the corresponding values of mode and RM fields. If you look into the table, mode equal to 10 and RM equal to 100 correspond to a memory location specified by SI plus a 16-bit displacement, and therefore we should have mode equal to 10 and RM equal to 100 to specify this. Now the displacement has to be specified. Displacement is of size 16 bits and the lower byte will be given in byte 3 of the instruction and the higher byte will be placed in byte 4 of the instruction. The lower byte of the displacement is 34H and the higher byte is 12H. Now putting all of them together in the instruction template, we have the first byte given by 10010 corresponding to the opcode of the move instruction. Then D is equal to 0 and W is equal to 1. In byte 2, the mode field is given by 10, the register field is given by 000, and the RM field is given by 100. Then byte 3 contains the lower byte of the displacement, which is 34H, and byte 4 contains the higher byte of the displacement, which is 12H. Then the hexadecimal code for this instruction is 89843412H. The next instruction involves a segment override. Consider move ds:43bp, cx. Here the source is the cx register and therefore can be specified by the reg field with value 001 and d equal to 0, saying that cx register is a source. Now the data transferred is of size 1 and therefore size 1 word, and therefore w should be equal to 1. Now the destination is specified by an offset address bp plus a displacement. The displacement here is only 8-bit long, so the destination is specified by bp plus 8-bit displacement. When we use bp to specify a displacement, the default segment that will be used is the stack segment. However, in this instruction we want to use the data segment. We want to use a location in the data segment with offset equal to bp plus 43. So if we want to do that, we want to use a segment override prefix. Now the segment override prefix have the most significant 3 bits and the least significant 3 bits set to a certain value, and only the remaining bits 3 and 4, called the S and R bits, as encodes the segment that is to be used. Now if we want DS segment to be used, we should set that 1 Now we have to look for the RM and mode values that specifies an offset address of BP plus an 8-bit displacement. If you look back in the table, a BP plus 8-bit displacement is given by mode equal to 01 and RM equal to 110. So mode equal to 01 and RM equal to 110 specifies a location with offset address BP plus 43. Now we want to use this offset in the data segment, and therefore we use the segment override prefix with S and R values equal to 1 and 1. Now the displacement is 43H, so that is given in byte number 3, which holds a value of the lower byte of the displacement. Now putting them all together in the template, we will have the segment override prefix with S and R equal to 1. Then the first byte contains the opcode in the most significant 6 bits. Then D should be 0, W should be 1, and in byte 2 the register field should be equal to 001, specifying the CX register. Then to specify an addressing with BP plus an 8-bit displacement, you should have mode equal to 01 and RM equal to 110. Then the displacement is specified in byte 3 as 43H. Now the hexadecimal code for this instruction will now be 3E894E43H.